Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today, we have Dr. Dylan Domel-White. Dylan finished his PhD under Bernard Bodman at the University of Houston, and now he's a postdoc at Vanderbilt University. We are happy to have him here today to tell us about one-bit phase retrieval. Take it away, Dylan.
All right, thank you so much, Joey and Dustin, for the invitation to speak yesterday, but I guess today we'll have to do. I'm really sorry to everyone here, and thank you for showing up today to listen to me. So yeah, I'm going to be talking about one-bit phase retrieval, first introducing phase retrieval, but then a sort of variation of that problem called one-bit phase retrieval, along with some algorithms and error bounds and guarantees for those algorithms. For one-bit phase retrieval. Okay, so this is joint work with my advisor, PhD advisor, Bernard Bodman at the University of Houston, and also Alex Powell here at Vanderbilt University. And so I want to start by just giving a brief introduction to phase retrieval. So phase retrieval, you know, it's we mathematicians have abstracted away a lot of the applications of this problem. But it is a problem that arises in a lot of physical applications. Namely, when you do some sort of you get some sort of measurement of an object, but you only get like the magnitude or intensity of those measurements rather than like the full, maybe complex valued measurement. And so here's like an example in diffraction imaging. You have like maybe some nanoscale structure, like maybe some crystal or something. You want to understand the structure of this very tiny object. And so you shine a beam of X-rays at it, and when it hits the object, that beam scatters and creates what's called a diffraction pattern, which you can see over here. And so that diffraction pattern is actually the modulus squared of the Fourier transform of the object that you're hitting with the beam. And so really, you want to get the actual structure of the object, not the modulus squared of its Fourier transform. If you actually had its Fourier transform, well, then you could just invert it and get the original object back. But since you have the modulus squared, you lost some of the information. You can't exactly recover the thing that you measured. So what you could do, though, is you could take multiple such measurements by introducing these, in this case, like phase plates or masks that sort of the diffraction pattern passes through, and you can get multiple of these images. And the idea is, with more data, maybe you can still recover something about the phase that you lost with your in your diffraction patterns. So that is one specific application of phase retrieval, and it comes up in many other settings as well. It's really closely related to some problems in quantum computing. Many others, but today I'll be talking more about one-bit phase retrieval. And so to get from phase retrieval to one-bit phase retrieval, really the big idea here is, well, a lot of the actual algorithms we have for phase retrieval, they maybe have some iterative process or something, and the initialization for that iterative process is very important. If you have a poor initialization, then that can lead to poor convergence. And so one reason that people started looking at like one-bit versions of a lot of these sensing and recovery problems is that maybe with these lower complexity measurements, we can more quickly come up with a good initialization, and then from there run a full precision algorithm. That's one thing, but also think of it in terms of just how much information are we allowed to lose, right? If you think of phase retrieval as losing the phase of the signals, what if I go even further and I lose much, much more and only get one bit of information, like a 1 or a 0? Okay. So that's our goal. We want to do phase retrieval from these one-bit measurements. And so the one-bit measurements, they're going to end up looking like this. We're going to have some signal here, x, and we're going to model our signal as a vector in a finite dimensional Hilbert space. And we're going to be getting one bit of information that sort of corresponds to the question, is x closer to a given subspace or to its orthogonal complement? So in this picture, x is closer to this guy. So this is sort of blue cone, and all those vectors in the blue cone there are closer to this subspace. So it's orthogonal complement. So I get one bit of information. Yes, it's closest to this one. That is enough. That on its own is not enough to recover X, right? If I only knew that, all I would know is it's something in this blue cone. But if I ask that question again for different pairs of subspaces, right, then I'm getting, different information about the location of X. And the idea is combine a whole bunch of these measurements to determine where X is, up to some degree of accuracy that you want. And so I'll be talking about two algorithms that do this and getting more into the specifics of those. So first of all, here's sort of the math formulation of the regular non-quantized phase retrieval problem. So we want to recover our signal X, finite dimensional Hilbert space, up to some ambiguity, which I'll talk about. And we model it in this way. We take inner products with some collection of vectors, and then we take the modulus. So we are, in fact, we're losing the phase of each one of these linear functions. Now, here are a few little observations about this problem. First of all, if you think of this collection of vectors here as just being a frame in FD, and I should mention F can be either the real or complex numbers here. So we are dealing in either real or complex finite dimensional vector spaces. So we're normally, like in frame theory, you're dealing with those frames and you get frame coefficients. And you can talk about quantizing the frame coefficients, or how do I recover the vector from these frame coefficients, which are the frame coefficients like the inner products of the frame vectors without a absolute value or without a modulus. And so here we are taking magnitudes of frame coefficients. So we're losing the phase. Can we still recover X? That's one question. What types of frames will work? And this ambiguity that I mentioned is that these magnitudes of frame coefficients, they will actually always coincide for signal X and for alpha X, where if I multiply X by any scalar with modulus 1, for example, -1, or if I'm over the complex numbers by I, when I take the modulus, these magnitudes of frame coefficients always coincide. So we could never distinguish signals that differ by one of these unimodular constants. And so instead, what we want to do is determine an equivalence class. This is the best we can do. We say, okay, well, there's actually a class of vectors that it's all the vectors that are unimodular constants times X, and we can at least hope to determine the class of the signal that we are measuring with these magnitude measurements. Okay, so that's really the goal, determine the class of X. And this can be generalized from frames of vectors to sort of the fusion frame version of the problem, where instead of magnitudes of frame coefficients, you take magnitudes of sort of fusion frame components. And in this case, if you think of inner product with Vj up here as taking like a one-dimensional projection of X, so giving you the components on a one-dimensional subspace of X, then instead we could look at components of X onto higher dimensional subspaces by projecting X onto a subspace Wj. And so without taking a magnitude, that would be in the realm of what's called fusion frames. And now taking a magnitude of that would be like taking a norm of that component. So norms of projections. We take norms of projections of a vector. Can we still hope to recover which class it is in? Okay. And so I'm going to be working with this generalization. Okay. And so now let me state what the one-bit phase retrieval problem is. So can we estimate a signal X? Now I've changed recover to estimate here because once we are quantizing this coarsely, we can never hope with just a finite number of these measurements to exactly recover the signal X that we're measuring. And I'll draw a picture to illustrate this in a second. But yeah, the goal now is estimate up to some level of accuracy that you want X up to the same ambiguity, and from one-bit quantized magnitudes. We take these magnitudes of projections, and then now we quantize. And we're gonna have to make an assumption here that our signals have a unit norm. So first of all, because of this quantization, we can't really hope to, we're gonna be losing information about the norm of X, so we just fix the norm to be 1. And then the question becomes, well, what sort of ways can we quantize? What are natural ways to quantize the regular phase retrieval measurements, magnitude projections? Okay, so here's 2 natural ways. First, I'd call thresholding. So really I'm just asking, is the magnitude of that projection greater than or equal to some threshold value tau? Yes or no, right? That's my 1 bit, 1 or 0. On the other hand, I could compare 2 magnitudes of projections. I could say, which one is bigger? Is PJ bigger or not, right? That's my yes or no. Is PJ bigger than PK? So these are 2 natural ways that we could quantize the phase retrieval measurements. And really there's a sort of natural setting where, so you could study either of these, but there's a natural choice for a threshold that then coincides with the natural choice of comparison. And that's really the one that we chose to focus on for our algorithm. So I want to highlight it here. If you pick tau to be 1/2, then using a threshold value of 1/2, that 1 bit question is equivalent to asking this 1 bit question where I use a projection PJ and I minus PJ is its complementary projection. So the projection onto the orthogonal complement of the subspace that PJ is projecting onto. And so this is a natural choice, and that's what we'll do. So this leads into that's the setup for the type of problem we're working with. Now I want to give you 2 solutions to this problem, 2 different algorithms that take that type of information, 1 bit quantized phase retrieval measurements, and tell you how to estimate the signal that was measured in the first place. So the first, I'm going to call PEP, or Principal Eigenspace Programming. Okay, so let's return to that choice for quantization that I mentioned previously. And here's a picture that you've already seen as well. And so I want to come back to this picture so we are clear on what this thing is asking. So since we're measuring unit norm signals, this threshold question is equivalent to asking whether the norm of PJ x squared was greater than or equal to, so these are also equivalent, norm of I minus PJ x squared. And that, just in plain English, is asking, or the answer to that question is really telling you, is x closer to the range of PJ than to the range of I minus PJ? And so here's a little picture to illustrate that. Again, if we have our vector x, and let's say the range of my first projection, P1, is this subspace, so here I'm in R2, then the norm squared of its projection is giving me, the norm of its projection is giving me this length, and I'm comparing that to projecting it onto the complementary subspace and comparing that to this length. So these 2 lengths here. And those are telling me about the distance of it from x to these 2 subspaces. Okay, so I do this for a whole bunch of pairs of projection, or a whole bunch of choices of the projection. And really what ends up happening is I get information about which of these subspaces x is closest to. Altogether, I can kind of narrow down a consistent region for x. I can narrow down, I can say, okay, if I take m such measurements, then where are all the vectors that match the measurements I made of x? Now, finding that consistent region is quite hard. Especially in high dimensions, I'm slicing up the surface of the hypersphere, high dimensional sphere. I'm sort of cutting it into these pieces with each measurement. I'm kind of taking the measurements in different orientations. Finding that consistent region for x might be difficult, but at the very least, you can hope that with enough measurements, you get a small consistent region and that you can get close to that in some algorithm. Okay. Now, this is a picture in R2, and I want to show another picture because I said we're not really trying to recover X. We can't hope to recover the exact vector X. We're actually hoping to recover its class X, the class of X. So there's a nice identification that you can make, which is that the class of X can be identified with the rank 1 projection onto the span of X. So since X is unit norm, if I take this rank 1 Hermitian XX star, it'll actually be a rank 1 projection. And there's a one-to-one correspondence between the classes we're trying to recover and these rank 1 projections. So at least in the case where the dimension of my signals is 2, this lets me view the projections that I'm using to measurement, PJs, and the signals that I'm measuring, X, all living in the same space, and I can actually draw pictures of those. So here's a picture of, on the left, of all the rank 1 projections in R2, also called the real projective line. So again, I might have some XX star class that I'm trying to recover. It lives somewhere on this real projective line. To measure it, I pick some projection. I picked, let's say, P over here. And on the real projective line, the complementary projection, the real projective line here is the circle, not the inside the circle, just the circumference of this circle here. The complementary projection is the antipodal point on the circle. And my questions are asking, well, which of these two is XX star closest to? And so in other words, which semicircle is it in? And different choice of P would get a different pair of semicircles. In the complex case, the rank 1 projections on C2 can be identified with the surface of the block sphere. Now, this is something that comes up in, I think it's used in mostly in quantum computing to model quantum states for a qubit. And the surface of the block sphere is all the paired states, or for us, it's all the rank 1 projections on C2. So again, if I have some XX star or a complex vector X in C2, it would live on the surface of the block sphere somewhere. Again, P and I minus P are antipodal points on the block sphere, and our questions are asking which one is XX star closest to. And so in this case, we're slicing it into hemispheres. And then we want to take different orientations of this to help narrow down a consistent region. So really, in higher dimensions, the picture gets a lot more complicated, but you can kind of use this to, this is at least morally correct. And what would happen is, well, I take more and more choices for the hemisphere, and that kind of slices up my, so let's say XX star I kind of drew over. Let's say XX star is over here. So as I take more and more measurements, I'm sort of slicing my sphere with these, equators or whatever. And there's some consistent region, and you could think that all the vectors around here that are the vectors that match all of the London measurements made of XX star. So if we could find that consistent region, that would be great, because that's actually the best you could hope for, right? And the best accuracy you could hope for with any estimation algorithm would be, it would depend on the width or the size or diameter even of this consistent set. So there's a lot of things going on here. You want to take enough measurements so that your consistent set becomes small, and then you want an algorithm that will find the consistent set, or at least get close to it. And so let's try to keep this picture in mind as I move. Okay, so like I said, we need to pick a lot of projections in different orientations in order to slice up the signal space we're looking at. And so how can we do that and make sure that we're slicing it up well, like that we're sort of nicely slicing it up and cutting down the consistent regions to be small? Well, simple answer would be to use sort of a uniformly distributed choice of projection. And so there is a uniform distribution on the projections, and it's just the rotationally invariant R distribution. It comes from the rotationally invariant, uniform distribution on the unitary group. And really, you can think of a random projection as being a projection onto a random subspace, and rotationally invariant here means, it's not biased in any particular direction. And so we should hopefully see the whole space if we take enough of these uniformly distributed projections. So we're going to use the uniform distribution. And so this leads me, let me outline what the measurements look like, so to summarize everything so far for PEP. So we take, for our projections, just a collection of independent, uniformly distributed. And here I'm specifying that I want my projections to be ranked d over 2, and d is the dimension of the singular. Now, the reason for that, and that's sort of kind of an artificial choice, you can like modify the type of measurements you're using and use projections in different ways. You can use rank 1 projections, but for the types of questions that I mentioned, where I'm comparing to 1/2, this 1/2 threshold really only makes sense for projections of rank half the dimension. If PJ were a different rank, then one of these, I'd be getting a 1 or a 0, like, okay, this is set up so that I get a 1 or a 0 with equal probability. And if I use a different rank projection, then one of these would be biased. It'd be like much more likely to get a 1 than 0. So really, you'd want to use a different threshold if you're using projections of different ranks. And then it wouldn't coincide with the complementary projection comparison. Okay. So yeah, but going forward, everything's going to be rank dimension over 2. So that's when we pick our projections. And then what are our 1-bit questions? Well, we ask for each projection is its norm squared greater than or equal to 1/2. And we record that in a big binary vector. So altogether, this BP of x, it's a binary vector, and its jth entry is telling me about, what happened in my threshold, the j projection magnitude. So this thing can look like this. And then the goal from there is, well, use that to get some estimate that we'll call x hat for the x that was initially measured. And really, we want for the class, right? And we're going to phrase this in terms of the rank 1 projections that we identified in this class. So really, when I state some theorems and stuff later, this is what we're going to be stating. We want this projection to be closest. Okay. So let's talk about the recovery. I told you how we measure. How do we recover? So first of all, we're going to encode this binary vector into some operators, I'll call PJ hat. And if you sort of unwrap this definition, this happened if that was greater than or equal to 1/2. And so really, PJ hat just picks out of PJ and its complementary projection. It picks the one that was closest to x, that had a range closest to x. And then we assemble all of these PJ hats into an operator Q hat. And this Q hat is just the empirical average of all the PJ hats. So we sum them all up and divide by the total number that we have. Okay. So we're going to use this operator to recover or to estimate x that we measured. Okay. So we let x hat be the eigenvector associated to the largest eigenvalue of Q hat. And so this is where the name principal eigenspace programming comes from, because to recover, we need to find the principal eigenspace of Q hat. And then our estimate for x is just going to, or our estimate for an element in the class of x is going to be x hat, right? Which is just any unit vector in that principal eigenspace. Okay. Why? Like, why would that work? So let's talk about that. So here's where, like, the magic happens. We expect this empirical average sort of point in the right direction. What do I mean by that? Well, if I take the expectation here, and this is with respect to the random projections that we picked. So x is just some fixed vector that we measured by picking random projections. I've made this Q hat, which now is a random matrix because it depends on these random projections. So the Q hat is a random matrix, and if I take its expectation, then it has this really nice spectral decomposition over here. And what do we see from the spectral decomposition? Well, we see that there's some eigenvalue u1 times xx star, which is the rank 1 projection in the span of x that we measured, plus another eigenvalue mu2 times the complementary eigenspaces. So really, this operator q of x has this two eigenvalues, u1 corresponding to the exact xx star that we want to find, and u2 corresponding to everything else, so the orthogonal complement of that. And moreover, the mu1 is going to be strictly bigger than mu2, and there's going to be a gap, a spectral gap that we can concretely bound between these. So we can really, on average, you could say like on average, we could distinguish where xx star is from every other dimension in space. And then to get from there, from on average, or the expectation, to what we actually have with our measurements, well, we can observe that, well, when we take an empirical average, if you take more and more measurements, you increase m, then the empirical average tends to concentrate around this mean, right? So we get tighter and tighter concentration around the mean as you take more and more measurements. And then the spectral gap that I mentioned between these two eigenvalues, we can use to bound, how far that's going to turn how far q hat is from q, and to how far x hat is from x, or x hat star is x star. Okay, that's sort of the idea, and maybe a little sketch of what the proof would look like. So let me give you, here is just in short that proposition about the expectation of q hat, but with just a little bit more information given to you. In particular, this says that the spectral gap we can bound, it's on the order of 1 over root d, and we have concrete bounds to this. So this is so I'm starting to get to our results from my paper with Dr. Bachman. Yeah, so that works out nicely, and this works for real or complex and in any dimension. Okay, and from that, we can get to, following that sort of proof sketch that I laid out, we can get to our first nice theorem. And this is what I would call like the pointwise theorem. So what's going on here is and the reason I'm calling it pointwise is that everything that we've talked about so far, we're kind of dealing with a single signal x. So that's why in this statement here, I'm kind of choosing, I'm assuming I have some x that I want to measure and reconstruct, and I'm kind of fixing that at the start. We fix that x, and then I have some constants here. Delta is the desired error level that I want. Rho is a failure probability. So both of those we want to be small, right? We want to be accurate, so small error, small delta, and we want this to work, like, we want to be pretty sure that it's going to work. So we want small failure probability, and then some universal constant c. And in the setup, if I take m, the number of measurements, to be on the order of, at least c times delta to minus 2, times the dimension d, times some logarithmic factors involving the dimension and the failure probability, then we can recover, with failure probability rho. This x hat, which is our principal eigenspace of q hat, is going to be within a delta of xx star. And let me add a little comment here. So this metric that we're using here, if you take two unit vectors and you look at their rank 1 projection on their spans, xx star and yy star, and this norm here that I'm taking is the operator norm of this operator, of the difference of these two projections. The operator norm of the difference of two rank 1 projections is the sine of the principal angle between. a span of. So let me draw a picture to kind of illustrate that. If I have two subspaces, span of x and span of y, then you can take the principal angle between them, and this operator norm is the sum of that principal angle. So it is, this is actually a well-defined metric on the equivalence classes that we're looking for, and it's a nice, concise way to talk about accuracy for phases. Okay. So again, this is what we call the pointwise bound, because the signal x has to be fixed at the start, and you generate your projections, measure, and then you know with a certain probability that this procedure, the PEP procedure, you take the principal eigenspace of Q hat, gives you something, gives you a class that's within delta of what you want. Okay, so that's great. That solves the original problem that we had, or a version of it. Now, the natural question is, well, if I generate these projections, is there a chance that like just one set of projections that I generate will work to recover any signal that I measure? So, so this is what we call the uniform theorem. And the idea is that we want just to generate our projections once and not have to regenerate, or want at least have a proof that says that we could recover any x that we measure from this measurement using a fixed set of projections that we generate. And that is a much more difficult theorem to reach. And I didn't outline yet what the proof strategy would look like, but it requires some more steps, and I'll go into it after this. But here's what that sort of statement would look like. It looks very similar. You have the same error level you want, failure probability you want, some universal constant C. And in this case, we end up needing more measurements. You can see in particular, there's a d squared that comes out here if you distribute. But now we get that this recovery holds for all x, for a single choice of the projections p that we generate. And to picture this, what I imagine is like, here's the sphere we had. If you generate enough uniform projections, the first theorem was saying that the consistent region we want, or that x is in, we're at least sure that that region will get small enough and that our algorithm gets close enough to it. And this theorem is saying, well, if I keep taking even more, then no matter where x is, I have sliced up the sphere enough that all the consistent regions are small enough and our algorithm will get close to it. Okay, so that is maybe a much more desirable guarantee or error bound to have in practice, because it kind of gives you the worst case, like a worst case bound. You know that everything will recover with this nice error level. Okay. So there, I haven't yet mentioned what was done previously, and I just want to mention here, like that there has been other work on one-bit phase retrieval with some with similar algorithms, and also the one-bit phase retrieval literature is very closely related to it and directly motivated from the one-bit compressed sensing literature. And so here I kind of give a comparison of how our theorems compare to previous theorems in this area. So this first row of this table is a paper by Quantum Machine on one-bit compressed sensing. So this is not a paper that was designed to do one-bit phase retrieval, but you can kind of massage things so that their results apply to phase retrieval, and you'd get that you need a number of measurements, on these orders here. Delta to the -4 times d is constant for pointwise, and delta to the -12 times d for uniform to get accuracy of delta. And then for a more specific paper that actually was looking at the one-bit phase retrieval problem is a paper by Rua and Sasko, where they get delta to the -4 d log d in the pointwise case, but they don't derive any uniform results. And so you can see that we were able to improve these bounds with a better delta dependence, and at least get a uniform bound for one-bit phase retrieval. which is really nice. And I'll like give you some pictures to kind of show how these things compare. So what's going on in this picture is the x-axis is the number of these 1-bit measurements that I take. And the y-axis is the accuracy delta that I get when I apply the PEP algorithm to recover and get x hat, and I measure how far away x hat star is from x star. And this is a log plot of that information. And here I'm showing pointwise. So each little, this like all these lines in black and white here, each one of those lines is sort of tracking the accuracy of recovery for a single x using some collection of projections. Here I did like projections. And then each line would be with a new random set of projections generated, because that's what we do with the pointwise. So you can kind of see that as I take more and more projections, we have this nice decay of the error. And the red line here is our error bound, which is roughly some constant. If you invert, I give you how many measurements in, you get delta. If you invert that to see what delta you get from a given m, you see that you get like around m to the minus a half. And the important thing to get out of this picture is that the slope of this red line looks like the slope of what we get in practice numerically, which means that this, we kind of get the right delta dependence in our theorems. This is all at a fixed dimension. So the dimension dependence of the m, that's a more difficult question to answer. We don't know if our our d dependency is correct or if you can do better, but at least the delta dependence looks right. The blue line is what the other things I was comparing to give, and I here notice I don't have a constant in front. That's also because they don't really give explicit constants in their papers, so I don't really know exactly what constants they have in front there, because they're more concerned with asymptotics. So here I'm just plotting into the minus 1/4. For the red line, I'm plotting with our explicit constant that we derived in our paper, and so that is what's giving this sort of vertical shift here. So there's also hope that you can improve that that constant, bring down the bound. So our theorem is saying that you should always get below this red line with high probability. Maybe you could bring it down. For the uniform accuracy, so here each black and white line is these black and white lines are all generated using the same set of projections. So I just generated one set of projections, took a whole bunch of different x vectors to measure using that set of projections. And again, if we compare to the Planen-Verschienen 1-bit compressed sensing stuff, it gets a delta to the minus 1/4. That you can see sort of has the wrong slope. And our bound with the minus 1/2 again has the right slope, at least for the delta dependence, except our constant is like really bad, right? So that's just what we were able to prove with an explicit constant in the paper. But so what you can kind of see here is that the asymptotics for delta look right. We don't really know about the asymptotics for the dimension d, and also the constant c could probably be improved. Okay, so that's a lot about the pointwise stuff, and the really the challenge for extending from the pointwise theorem to the uniform theorem is that, well, I'm gonna say here, there's a lack of continuity in this q hat operator that we were assembling. So yeah, if I know that my algorithm works for one fixed x, I could use with a certain probability, and use a union bound to say it'll work for like a whole bunch of different choices of signal x that form like maybe an epsilon net of our signal space. But then extending from that epsilon net is not obvious how to do that. And so our approach there, we used a similar strategy. We got this idea from the Planen-Verschienen 1-bit compressed sensing stuff, where, and so I kind of show it to you here. I'm gonna skip ahead a little bit. So what our measurements were looking at seeing before, right? If I had like a vector x and a vector y, I could say from our 1-bit PEP measurements, I could say that they, if they had different measurements, if I got a 0 for p sub 1 for x, I got a 1 for p sub y for p sub 1 when I measured y, that would mean that like one of them gave me some magnitude squared over here, like between 0.5, and one of them gave me a magnitude squared over here from 1/2 to 1. And that's all I know, that one of them is on one side of the threshold, the other's on the other side of the threshold. And they might actually be really, really close to the threshold, right? They might both be on different sides of the half, the threshold value, but might be really close. And so the soft handing distance idea is, well, just sort of add like a buffer. Instead of just determining whether you're getting different threshold values, determine if you are you're on different sides and far enough away from a half. And if you have that, then it kind of gives you an extra parameter you can, that kind of you can tweak in place of continuity of the Q hat. So I won't go into the specifics here, but it leads to a nice way you can prove in the spirit of saying that for any two big enough measurements, for any two vectors x and y, the number of 1-bit measurements that are different for them is bounded by the distance between. And that's uniformly, that's true for all pairs of x and y. So that is key step to extending the pointwise space to uniform. Okay, so that's just kind of showing, I just want to illustrate that even in these 1-bit non-continuous measurement settings, there is hope to get the uniform bounds, and that this T-soft handing distance stuff is the way to do it. I don't have time to go into more detail. Okay, so the second algorithm I want to talk about called ICQPhase. And so this is work with Alex Powell here at Vanderbilt. ICQPhase stands for Iteratively Consistent Quantized Phase Retrieval. And I'll just start by showing you a picture here. So this is some other algorithm. It's like an iterative algorithm. And what I'm showing you here is that it's converges faster than PEP, which is great. So what's going on in this picture is, again, I have the x-axis is the number of measurements in, and the y-axis is, in this case, a squared error. After for using in measurements, and PEP is this blue line, and this ICQPhase algorithm that I haven't defined yet is this red line. And so we see, it's sort of this initial regime where PEP is doing better, but eventually ICQPhase kind of hits its stride and starts converging much faster. And so what it looks like is happening is that, well, for PEP, we know that if we use in measurements, we get, I didn't phrase things in terms of mean squared error, but for in measurements, the mean squared error is on the order of 1/n. And ICQPhase looks like has a mean squared error on the order of 1/n squared. It's much better, converging much faster, at least once you pass this initial hurdle. So let me define what this algorithm is and tell you what we know about it so far. So this is still something that we're investigating, but and I can give you some of our first results on it. So ICQPhase. Okay, good. So ICQPhase, we are starting with the same types of measurements that we were using in PEP. So this phi sub p, we're still using the rank dimension over 2, randomly chosen uniform projections, thresholding at a half. And this is just a different way to estimate x using that same information, but hopefully does so faster. So we take an initial estimate x0, and then we define this iterative procedure. And here's what happens at the j step. So we measure our current estimate. So if we're trying to update to xj, that means we currently have xj minus 1. That's our current estimate for x. And we measure it using our projections. Really, you only have to take one measurement of it. You take use the jth projection to measure. And you get your 1-bit, 1 or 0. If that matches the jth 1-bit measurement of the original signal x, then that means that using that jth bit of information, there's not really anything, we can't really improve our current estimate because it matches what we know from that jth one bit of information. So we wouldn't change it. On the other hand, if it doesn't match, then we do some update. And here's the update. And I'll talk more about what this is doing, but it gives us some unit vector that is consistent. And the whole idea is that we're kind of updating it to become, if it wasn't consistent, we update it to become consistent with that j one-bit measurement of x. Okay, and we want to do that in a clever way because, you know, if this is the jth step of an iterative process, we don't want to update and break everything that we've done in the previous steps. So we need to make a smart update that incorporates the new information that we have from the jth measure. Okay, so we do that in the time, and let's call x tilde the results of that procedure. The goal is, or the idea is that x tilde should be a good estimate for x. Okay, so here are some observations about that procedure. So first of all, this update, if we make that update, what it's really doing is it's finding the closest vector to xj minus 1, to our current estimate, that is consistent with the jth one-bit measurement. Okay, so the idea is maybe your x, it lives in this, like, in that consistent region we've been talking about. And maybe here is my xj minus 1. It's not yet in the consistent region. And so maybe this yellow line, maybe this is sort of the boundary between the that you know we're slicing the sphere into, that sort of equator that I was drawing. Maybe that's the slice that we make with the jth one-bit measurement. Okay, and so we see when we are running our iterative procedure, okay, they're on different sides, right? They don't match. If they were on the same side, that would mean they'd have the same one-bit measurement from this yellow, from this yellow projection. So they don't match. So what do? Well, we find the closest vector in the consistent region. Now, this is just in the consistent region for this one single one-bit measurement. So the consistent region for that would be everything on this side of the yellow line. Okay, so we make the minimal update to reach that consistent region, and that would put us that would put us over here. So now I am, you know, at least consistent with the jth measurement. I'm still not in the consistent region, but I've sort of like crossed one more of those lines, one more of those boundaries. And the idea is if I do that enough, like if I were to next cross this line here, then it would put me right where I want to be, right? And it's important that to note that this, you know, since we're only enforcing consistency with a single measurement, that we might break previously enforced consistencies, like from previous steps. But the fact that we're making this smallest update to become consistent means that hopefully we won't break them by too much, right? And so by making enough of these, hopefully we at least will get close, even if we're not perfectly consistent. Some other nice features of this feature is that it uses the data in a streaming way, which means that if I've done this for my in measurements, if I then decide I want better accuracy, I can just kind of continue from where I left off. I can just take new measurements of X and continue updating. And whereas PEP kind of required using all of the measurements at once, right? So that's a nice feature of it. But some downsides are that if it's, you know, we're projecting a unit vector onto a set on the sphere, and the set is non-convex, and so, you know, analyzing how this converges is not obvious. And also that we have to remeasure, we have to determine whether our current estimate is consistent or not, which means we have to estimate the current estimate, or it's not estimate, we have to measure the current estimate, which is something that have to do. But that is a very small, you know, overhead to add. So here are just some numerical pictures showing numerics of this procedure. The dashed line is square is 1 over n squared, and the blue line is the squared error from using ICQPhase. And this is in a bunch of different settings, in both the real and complex setting and in the different dimensions, d2, 10, and 20. And so you can see that, yeah, eventually this procedure does seem to reach the 1/n² convergence, but it has this sort of period where its convergence slower. So that seems to get to be extended as the dimension grows, but seems to be dimension dependent. And here is sort of the theorem we have. We decided to start looking at this in the simplest possible case, which would be real phase retrieval in R2. And so here is a very precise error bound for this procedure. And we see that the mean squared error, when we do ICQPhase, we get x tilde. When we, after m steps of ICQPhase, we have this first term that dictate we have an m squared, so 1/m², and some constants and stuff. So we do get mean squared error on the order of 1/m². And then this term is sort of exponentially decaying in m, since we have the 7/8 to some power of n. So this term goes away very quickly, but this term might be what is a term that probably governs that sort of initial phase of the convergence. Convergence slower in higher dimensions. But the higher dimensional and complex cases, we've tried to look at them, but it's quite difficult, and we've bashed our heads against it for a while. And yeah, so we made a little bit of progress, but we don't have a theorem. So that's where we are. That's sort of a second algorithm that seems to work. There's a lot to do there. Higher dimensions, complex case. What's the dimension dependence? And also, I've been phrasing things for ICQPhase in terms of mean squared error. What about getting these high probability bounds or uniform bounds instead? Okay. And yeah, I'll stop there. Thank you guys very much.
All right, thanks a lot, Dylan. We'll all express our feelings with buttons. There's mine.